Yeah. So, yeah, I understand there are multiple questions on homework 7 as well, particularly because it sometimes deals with PMOS transistors, and some of you might have a little bit of confusion on PMOS transistors. But then again, the best way to deal with PMOS transistors is that you use the same equation as your NMOS transistor, but remember that the drain becomes source for a PMOS transistor. Or what is the direction of current flow in an NMOS transistor? You know that already, right? It's from drain to source. Why? Because remember that from your device physics, the charge carriers will always flow from source to drain. For an NMOS, the charge carriers are electron because N is negative. N stands for negative. P stands for positive in a PMOS. If N stands for negative, you have your charge carriers as electrons. And electrons will flow from source to drain, which means that the current will flow from drain to source for an NMOS. For a PMOS, it's exactly the opposite. You have your P-type charge carriers or positive charge carriers, which are the holes. And holes, again, flow from source to drain because source is source of something. Drain is, again, sink of something. Right? That definition, the definition of the English word does not change, depending on whether it's a PMOS or an NMOS. Now, if the charge carriers are flowing from source to drain for the PMOS, the current will also flow from source to drain for the PMOS because it's positively charged carriers which are flowing from the source to drain. So for PMOS, you'll see that the current flow is from source to drain. Remember, this is the source terminal. And that's why you see that in the symbol, the arrow is pointing inwards because at the source terminal, the current goes in and comes out of the drain terminal. So remember this basic difference between your PMOS and your NMOS. For your NMOS, current flows from drain to source. For the PMOS, current flows from source to drain. And that is another way of saying that the source terminal will be at a higher potential for PMOS. On the other hand, the drain terminal will be at a higher potential for NMOS because current always flows from a higher potential to a lower potential. You cannot make current flow from a lower potential to a higher potential. Okay. So if that is true, the way you should analyze any kind of PMOS-based circuit is as follows. So for your NMOS, you know that if your VGS is more than the threshold voltage, then the transistor is on, right? That's for your NMOS. For your PMOS, what you need to do, just take absolute values. Absolute value of VGS has to be greater than the absolute value of threshold voltage. Then the PMOS transistor is on. If it is not the case, the PMOS transistor is off. Similarly, what is the equation for saturation in an NMOS? The equation for saturation in an NMOS is that your VDS has to be more than your overdrive. Okay. So your VDS has to be greater than your overdrive. So again, take the same thing. Take the absolute voltage of VDS, which will be equal to VSD for a PMOS. Because remember, for the PMOS, the drain potential is at a lower voltage than the source. So VDS is negative for a PMOS, but VSD is positive. Also, the absolute value of VDS is positive. So you just take the absolute value. That makes your life much simpler. So that's it. That's all the equation that you need to apply for a PMOS. Now, how to solve these kind of problems is that again, for this, it is given that the threshold voltages are minus 0.75 volt. Because again, you know, for a PMOS, the threshold voltage will be negative because you need to attract holes in the channel so that you can create a channel below the gate, right? So that's again coming from the basic device physics of the PMOS. The values of K is given. You're asked to neglect lambda for now for the first question, which means that you don't have any kind of channel length modulation and your R out is infinity. Remember, R out or the output resistance of the transistor or the drain to source resistance of the transistor, that is equal to 1 upon lambda ID. And that is a formula you'll be using for, I think, question number 3, where lambda is given to be a non-zero value. If lambda is non-zero, 1 upon lambda ID is not an infinite value. And 1 upon lambda ID is your RO for the transistor. So that is something we'll be using for the later part of the homework. Now, the first part is very easy. You have already solved these kind of problems in your exam, as well as homework 4, as well as homework 5. So it's nothing different. The only difference is that you now have to take an absolute value to make sure that these equations hold true, right? That's the only one and only difference. That's it. It's as simple as that. So if you have any kind of confusion on how to solve these problems, remember that you just have to take the absolute value. And why is that? Again, coming from the device physics, that the source potential will be at a higher potential than the drain for the PMOS, whereas it was the opposite for an NMOS. Okay, so that is, I guess, one part of the confusion was. The other part of the confusion that I got from the questions posted on GroupMe is that what is the meaning of having this lambda equal to 0.04 volt inverse? How do we use this information? And how do we actually use this information is that your RO of the transistor, as we just mentioned, is equal to 1 upon lambda ID. Again, something that we have proved from your small signal models. So if you don't remember this, please go back to your small signal model. Please go back to the lectures where it was discussed and proved, and use this formula to find out the RO of the transistor. Questions? Mm-hmm. 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 That's right. You just need to have the lambda factored into it. So when you are using the equation in your saturation should be that your current is equal to K over 2 P overdrive squared times 1 plus lambda times the absolute value of VDS. If you're using this equation and then using this equation, if you have taken this partial derivative, then you're right. Okay. And basically RO equal to 1 upon lambda ID, this equation comes from doing the partial derivative of this particular equation, right? So if you remember the proof, yeah, Alessandro. Yeah. I mean, as I said in the beginning of this course, that you can have 10 different approaches, and you might see that in your homework or in exam. Everyone, or like many of you, are following many different approaches, and all of those approaches are correct as long as you're understanding the logic behind, right? So you can use the small signal approach. You can use some of these formulas which you derive from small signal approach. You can start from a large signal approach and then take the partial derivative, which is the way to derive the small signal from a large signal equation. So there are multiple approaches, and all of those approaches are correct as long as you understand the logic behind. Okay. All right. So I think one other important question that came up is that up to this point, I guess, if you're with me, that the way to solve these kind of problems is just to take an absolute value on the equations that you have already learned. I'm hoping that you should be able to solve question number 1 and question number 2 correctly. Okay. If you have any questions, just let me know. Now, question number 3 is a little bit more intricate. It has a little bit more thinking to do. And what it says is that it gives you all these values of threshold voltage, K2, K3, K1, and so on. But eventually, it asks you to find out the gain, right? So this gain AG is dV out over dVG1. And in this case, what you really had is this particular circuit. Now, what is this circuit? Your input is applied at the gate of this transistor, right? Your source is grounded, and you're taking your output at the drain. So that's basically a common source amplifier. Okay, so that's your common source amplifier. But what is the load to your common source amplifier? The load to your common source amplifier is the resistance that you see looking into the drain of this top transistor. So it's nothing different from this structure that you had learned before, that you have a common source amplifier, you apply your input at the gate, you take your output from the drain, and at the drain side, looking up, you'll see a resistance connected, right? That's the basic common source amplifier you have learned. This is nothing different from that. It's the exact same circuit. Why I'm saying it's the exact same circuit? Because looking into the drain of a MOSFET, you do see a particular amount of resistance. And again, from your small signal model, we know how to find out the resistance looking into the drain of a transistor. Okay. Now, looking into the drain of the transistor in this case, this was a PMOS, we are looking into the drain of that PMOS. The resistance that you would have seen for question number 2 is basically equal to RO. Because remember, looking into the drain of a transistor, you see RO. looking, unless the transistor is diode connected. If it is diode connected, you see 1 upon Gm. We proved that as well. But if it is not diode connected, in this case, you have a current source load. This is the way we had defined it earlier, that you have a current source on this side. You are mirroring that current on the right-hand side through this current meter structure. So this is your current meter structure. So what you really have is basically a current source connected on top. So you can also model it as a current source connected at the drain of this transistor, right? So this is another model of what you have over here, that you have a common source amplifier. The load that you see for that common source amplifier is basically a current source. Now, of course, a current source ideally has infinite resistance, but you know that everything is non-ideal in this world. So the current source will also have a parallel finite resistance, and that parallel finite resistance is equal to RO, right? That's what we have learned when we represented the transistor as a current source in saturation. Remember, in saturation, the transistor works as a current source. The current through the device, if this is current and this is VDS, the current through the device saturates in this region, in the active or saturation region. So whatever your VDS is, you have a fixed amount of current. If you have a fixed amount of current, the transistor is basically working as a current source with a fixed amount of current, right? So that's why all of these things, all of these different concepts that we are talking about, they fall into place because you can represent the resistance looking into the gain of this transistor as RO. You can represent that as a non-ideal resistance of the current source that you represent with this current meter structure. And you can also represent it just with a resistance, with a value of RO. All of those approximations are correct. Again, as I said, that you can approach the problem in multiple different ways, but all of them are correct. Okay. So now looking into the gain of this transistor, you see a resistance of RO. And how do you find out RO? You find out RO by applying this formula, RO equal to 1 upon lambda ID, or you just use this formula, take the derivative of this ID current with respect to VDS, and then you can find out RO, and you'll end up with the same equation, 1 upon lambda ID. So that's the resistance that you see looking into the drain of this transistor. Question? I2, yes. So you have to consider the current that is flowing through that particular transistor. If it is some other transistor, it does not matter, right? There could be 100 other transistors in the circuit. You have to consider the current that is flowing through the transistor that you want to analyze. You want to analyze this transistor. So you have to consider the current that is flowing through this transistor, not any other transistor. Okay. All right. So why this problem is a little different than the previous one? It's because all the DC points or all the way, the approach that you should take to do the DC analysis is exactly the same here. The only difference is that at the source, you have these resistances connected. Now, if you have these source regeneration resistances connected, remember that this is the source terminal of the PMOS. So this is connected as a resistance at the source, right? Question?
For the previous one, also?
Yeah.
Shouldn't the gain end up being
Dm times RD?
You get a negative Dm times RD in parallel with RO, right?
Yes. Yes.
So it technically would be like negative Dm.
Technically, the gain in this case should be minus Dm1 times
RO1 in parallel.
RO1 in parallel with RO2. That's right. You're perfectly right with that. That the resistance that is connected at the drain terminal over here, that is not only the resistance that you see looking up. Remember that if you again, I would say that always keep this MOSFET cheat sheet handy. Always keep this cheat sheet with you. This will give you an idea about how to analyze or what to analyze for different systems or different circuits. So, for example, this is your basic common source amplifier, right? And we already mentioned that the gain is Dm times R out, and if RO is infinity, then the gain is minus Dm times RD, right? Minus Dm times RD. If RO is not infinity, gain is minus Dm times RO in parallel with RD, but RO is the R out of this particular transistor. Okay. Now, what is RD in this scenario? The RD is the resistance looking up. That is RO of the second transistor. So that's RO2. So you basically have RO1 of the original M1 transistor in parallel with the RO2 of the other transistor. So that will be your exact form of the gain equation in this case. So you're right. In this case, what is the difference? The difference is that looking up at this point, looking into the drain of this transistor, you'll not see RO. You'll not see only RO. Why is that? Again, you can do the entire small signal analysis that, okay, looking into the drain of a transistor. Let me see where I have this one. Yeah, here. So looking into the drain of a transistor, and if there is a source resistance connected, then what is the resistance that you see looking into the drain of that transistor? If RO of this transistor is infinitely large, you just see an infinitely large resistance, right? So you can just represent that with RO. But if RO is not infinitely large, if it is a finite quantity like you have in the problem, RO is equal to 1 upon lambda ID, then the resistance that you see looking into the drain of this transistor is basically RO of that transistor plus the intrinsic gain of the transistor, which is GM times RO. The intrinsic, you know that GM times R is a gain quantity. The intrinsic gain of a transistor is the intrinsic GM of the transistor multiplied by the intrinsic resistance of the transistor. And the intrinsic GM and intrinsic resistance of the transistor are just GM and RO, right? So this is called the intrinsic gain of the transistor. Even without any external component connected, this is the gain that you can expect from the transistor itself. So 1 plus GM RO times RS. So it's as if this resistance connected at the source gets multiplied with the intrinsic gain plus 1. And plus 1 is just to make sure that mathematically we are correct. You can also approximate it to be just GM RO times RS. And that would be the resistance that you see looking into the drain of the transistor. What is the proof? The proof is shown here in the next 2 pages. Okay, so just go over the proof. If you still don't understand why the resistance looking into the drain of the transistor will be RO times the gain of the transistor multiplied with RS. And that's what you have to do for this particular homework problem. Question. That's a very good question. Let's see if the GM is given in this particular one. I don't see the GM given, but you know what is the value of GM. GM is basically K times DOV. So if you can, I guess you already found out the overdrive voltages for both of these problems. So if you know DOV, K is given. So K times DOV is basically your GM. Right? K times V overdrive is equal to your GM. So that's how you should find your GM in this case. Okay. Now, yeah. Mm-hmm.
So in that case, I found out that the drain voltage.
Yeah.
I'm not first one is the current report because it's something like it's because the drain current
Right.
the RS2
Right. Yeah, but you already know what is the current flowing through this path. You already know what is the current flowing through this path. That current multiplied with that resistance will give you the voltage drop at that rate. So that's a simpler way to analyze it. Yeah. So what is the only change that you'll see in this case? The only change that you'll see for question number 3 with respect to question number 2 is that the resistance looking into the drain of the N2 transistor will not be equal to RO. It will be equal to RO plus GM RO times or 1 plus GM RO times RS. And you already know what is the value of GM for that particular transistor. You already can find out what is the value of RO for that particular transistor. You already know the value of RS. So you already know what is the resistance looking into the drain of that transistor. Okay. So that will be the change that we'll see in this case. And you'll see that the gain for question number 3 will be much, much more than the gain for question number 2. For question number 2, this will have a lower gain. Question number 3, you'll see that the gain will increase because of this multiplication of RS2 with GMRO and then getting it added with the RO resistance of the transistor itself. Again, the proof is given in the cheat sheet. So go over the proof if you're not convinced that this resistance increases as you look into the drain of the transistor. Okay. Any other questions? If not, let's continue our discussions on differential amplifiers. All right. So you know about differential amplifiers by this time, and you already know that. Maybe let me go back to a simpler looking figure for the differential amplifier. So you already know that this is how your differential amplifier looks like. This is one of the differential branches, which is a common source. And again, this is the other differential branch, which is again another common source. So that's it. Again, all your analysis for your common source amplifier will hold true for the differential amplifier as well. And remember that this point P is an AC ground. This point P is an AC ground because if you have a sine wave at the gate of the M1 transistor, at point P, because of this sine wave, this part of the system works as a source follower, right? That if you apply a signal at the gate and you're looking at the effective signal, because of application of the other signal at the gate, you'll see a source follower type operation. Because your input is at the gate, you're looking at the signal at the source, so it will work as a source follower. So it will be exactly the same signal that you apply at the gate. On the other hand, on the other input, you apply a differential version of the previous input. So the M2 transistor and the source of the M2 transistor will result in another source follower operation. So at the source of M2, you will see exactly same as what you have applied at the gate of M2. Now, look into this figure in a little bit more detail, that the source of M1 and source of M2 are connected together, which means that the voltage that you create because of application of the voltage at the gate of M1 and the voltage that you create because of application of the voltage at the gate of M2, those two will add up at the point P. And if these are fully differential versions of each other, they will compensate each other. They'll just complement each other. And if you add a positive sine wave and a negative sine wave, you get no sine wave at all. You just get a DC. That's why we say that this point P is an AC ground. It does not have any AC signal. It's just a DC point. Okay. So remember that while you are doing any kind of half circuit analysis for the differential amplifier. Okay. Now, what we wanted to discuss here was differential pair with MOS loads. So in the previous circuits, you saw that all the differential pairs had resistances connected as loads. But instead of resistances, you can connect MOSFET as a load, right? Because you already know that looking into the source or the drain terminal of a MOSFET, you'll see a particular amount of small signal resistance. So for example, here, if you replace that resistor with a diode connected MOSFET, again, remember that this is a diode connected PMOS. Your gate and drain of the PMOS are connected together. So that's called the diode connected configuration. And we already discussed why it is called diode connected. It lets current flow in only one direction and does not let current flow in the other. That's why it's called the diode connected configuration. Now, looking into the diode connected configuration, the resistance that we see is basically 1 upon GM, right? The resistance looking into the diode connected configuration is 1 upon GM. So what would be the voltage gain in this case? Again, remember that voltage gain in this case will be of the form GM times RD. Now, what is the GM that, or if you want to be more exact, it would be GM times RD or GM1 times RD because M1 is this input transistor. So GM1 times RD in parallel with RO1. So if you wanted to be more exact. But since RO1 is much, much larger than RD in this scenario, it's okay to assume that the gain is just GM1 times RD. Why I'm saying that R1 is much, much larger than RD? Because the value of RD is 1 upon GM. That's the resistance looking into the diode connected MOSFET. So what you really have is basically minus of GM1 times 1 upon GM3 in parallel with RO1. Now, RO1 is usually in the range of hundreds of kilo ohms or at least tens of kilo ohms. On the other hand, GM, the value of GM you have seen in your homework problems is a few millisiemens. So 1 upon GM is in the range of kilo ohms. So if you have a kilo ohm resistance in parallel with 100 kilo ohm resistance, you effectively only have the effect of the 1 upon GM, right? So the RO will not even matter. RO is as good as infinity in that case. So that's why you see that the gain equation becomes minus of GM of the NMOS transistor. So that's GM1, or you can also call it GMN because that's the GM of the NMOS transistor, divided by GMP, which is the GM of the PMOS transistor or N3 transistor. So your gain becomes a ratio of the two GMs. Again, you cannot achieve a very high gain because having a very high ratio of GMs in the two transistors is not practically that much feasible. You cannot have a ratio of 100 between these two GMs, right? So in your homework problems, did you ever see the GM of one transistor being hundreds of millisiemens and the other one being microsiemens? You did not, right? And that's only because the W over L of the transistors does have a physical limit when you actually place them in a chip, in a circuit. So you cannot have a very high gain for this particular circuit, but we already know what is the solution to that, how to have higher amount of gain, and that is by having, so let me skip some of these. Okay, so let me skip some of these slides, but something important that I wanted to tell here is that instead of having the diode connected load, if you had a current source load, what is meant by a current source load is that instead of diode connecting the gate terminal to your drain terminal, instead of doing this connection, if you had connected it to a bias, so let's say M3 is connected to a bias, M4 is connected to a bias, and that bias can come from a current source once again. So you can have this type of a circuit connected on the left side over here, that another PMOS is connected here, and you're mirroring a current to that PMOS circuit into the gate of the M3. Okay, so you're mirroring whatever current is going in this branch into this branch. So that's why it is called a current source load. And you have looked into current source load for common source amplifiers already. So again, this is nothing different. It's exactly application of the same ideas for a differential amplifier. Now, if you have that instead of having a current source load, the resistance looking into the drain of this M3 transistor will be RO, right? Instead of 1 upon GM, it will be RO. And as soon as this becomes RO, your gain equation will become minus of GM1 times RO1 in parallel with RO3, right? So this RO1 in parallel with RO3, that's a much larger resistance than just 1 upon GM3. And that's why you can increase the resistance of this particular differential circuit as you look into the drain of the current source load instead of having a diode connected load. So at this point, I'll stop, and just like we did the summary for your common source, common gate, and common drain amplifiers, I have prepared a summary for your differential amplifier. So I'd like to go over that at this point, but please go over the slide and let me know if you have any questions. Okay. So for differential amplifiers, again, this summary document is uploaded in your campus. So what we really have for your differential amplifiers is that you have one common source amplifier on the left side. You basically have another common source amplifier on the right side. Your inputs are differential versions of each other. That means they are 180-degree opposite. They have 180-degree opposite phases. The outputs will also have 180-degree opposite phases. And that's why when you take a difference of those signals, it becomes double of the individual signals. So if you had two sine waves which are exactly at the same phase, the difference of those two signals is 0. On the other hand, if you have two signals which are opposite phases, 180-degree opposite phases, the difference of those two signals is the double of each of the individual signals, right? That's the idea of a differential amplifier. So your Vout1 and Vout2 are amplified version of Vin1 and Vin2, and the difference of Vout1 and Vout2 is the differential output for your differential amplifier. So your input Vin will be basically your Vin1 minus Vin2, and your final output will be Vout1 minus Vout2. So that's your equation for gain, differential mode gain, which will be equal to the difference of the two outputs divided by the difference of the two inputs. That's called a differential mode gain equation for the differential amplifier. Now, of course, Vout1 minus Vout2 is equal to twice of the individual Vouts, and Vin1 minus Vin2 is equal to twice of the individual Vins, right? Just because it's the same logic that we applied over here, that the difference of two signals which are at the same phase is 0. The difference of two signals which are 180 degrees out of phase is twice larger than each of the individual signals. Now, if that is the case, then the differential mode gain is nothing but Vout over Vin of each of the branches. And you know each of the branches is a common source. So the overall differential gain is equal to the individual gains of each of the differential input branches. So each of the common source branch, whatever gain you have in each of those branches, that would be the overall differential gain as well. The point Vp, that's a virtual ground. So this point is a virtual ground when your Vin1 is equal to minus of Vin2. That is, Vin1 and Vin2 are 180 degree opposite phases of each other. There is also a concept of common mode gain, which we discuss a little bit. What does common mode gain mean? Common mode gain is Vout1 minus Vout2 divided by Vin, when your Vins are equal. Let's say you are applying the same signal. Let's say this is your Vin1 and this is your Vin2. You are not applying the 180 degree out of phase signals. You are applying the same signal at the inputs. If that is the case, ideally you should not see any output as well, because ideally your outputs will also be the same, and as you take a difference of those two outputs, you'll see 0. But practically, because the two branches will not be perfectly identical with each other, there would be some mismatch in the transistor properties. There would be some mismatch in the resistances. For example, let's say these are 10 kilo ohm resistances. One of them might be 10.01, other one might be 9.99. Because of those small differences, you'll see that the differential output will not be 0 in this case. And you'll see a finite differential output. Vout1 minus Vout2 will not be 0, it will be finite. So Vout1 minus Vout2 divided by Vin, when Vins are equal, Vin is equal to Vin1 equal to Vin2. That is called the common mode gain. This is something we did not discuss in a lot of detail, but as you look into any op-amp, if you look into the data sheet of an op-amp, you'll see something called a common mode rejection ratio. This is the idea of the common mode rejection ratio, that CMRR or common mode rejection ratio is 20 times log base 10 of the differential mode gain divided by the common mode gain. So how big your differential mode gain is as compared to your common mode gain, that tells you something about your CMRR. Why CMRR is important? Because remember, noise is a common mode signal. If you apply same amount of noise at the two inputs, you ideally would have expected that there is 0 effect on the output. But there is some effect on the output because things are non-ideal. And you'll see a finite ACM. You'll see a gain which is not 0. You'll see a non-zero gain for the common mode scenario. And that's why CMRR is very important. That tells you about how much the system will be affected by noise, how much the system will be affected by any kind of power supply variation, how much the signal system will be affected by interference. Let's say you have all these fluorescent lights, they will have some kind of interference on your system. You have FM in the range of 88 to 108 megahertz. That will have some kind of interference. All those interferences are also common mode. So how much your system has a common mode gain, on that it will depend that what would be the effect of your interference on the system. And that's why the CMRR quantity is very important for any op-amp or any differential amplifier. You already did the half circuit analysis. You know that you can represent this differential amplifier with just the half circuit, with the source being a virtual ground and we have discussed why this will be a virtual ground. The gain of the common source amplifier is minus of GM times RO in parallel with RD. That's again the exact formula that you mentioned. But if RO is much larger than RD, this can be approximated as minus GM times RD. And that would be the gain in your differential amplifier as well. Okay, Diff-Amp with diode connected load. Again, something that we saw right now, that let's just assume your GM1 is equal to GM2. That is the gain of the GM of M1 transistor equal to GM of M2 transistor. RO1 equal to RO2, GM3 equal to GM4, and RO3 equal to RO4. What this means is that the left side branch is identical to the right side branch. Again, just an assumption, may not be true in a practical scenario. So your AV, that's the voltage gain, that would be equal to minus of GM times RD in parallel with RO1. What is RD? That's the drain resistance that you see connected at the M1 transistor. So the resistance connected at the drain of the M1 transistor, and the resistance looking up at this point is equal to 1 upon GM of the M3 transistor, because M3 transistor is diode connected. So that's why the drain resistance is 1 upon GM3. Okay. So the gain in this case will be minus GM1 by GM3, which will be also equal to minus GM2 over GM4, because we have assumed the left side branch is identical to the right side branch. In reality, you might see a small difference, but yeah, I mean, your gain will not be very different. So using this formula, if you expect a gain of 5, in reality, you might see a gain of 4.98. And that's as good as having a gain of 5. Okay. Okay. Now, if you have active load or common or current source load, that means that instead of making these transistors diode connected, you bias them separately. So you apply a bias voltage, or you connect them using a current mirror structure, something like what we had drawn in the class a little while ago. Or what is given in your homework 7 problems as well, that how do you bias these PMOS transistors using the current sources that will be connected on the left side or right side. So let's just say these are biased separately, and in that case, the resistance looking into the drain of the M3 transistor will be equal to RO of the M3 transistor. So the overall gain in that case will be minus GM1 times RO1 in parallel with RO3. So you take the half circuit again, you do not need to analyze the full circuit. For this half circuit, which is again a common source, the gain will be GM1, which is the GM of the input transistor, multiplied with the resistance that's connected at the output terminal. What is the resistance that's connected at the output terminal? It's a parallel combination of the resistance that you see looking up and the resistance that you see looking down. The resistance that you see looking up is RO3. The resistance that you see looking down is RO1. A parallel combination of those two will give you the effective resistance at the output terminal. Now, this gain is much more than the scenario with diode connected load, because with diode connected load, you just had 1 upon GM. That's much lower than having a resistance of RO. Okay. Now, there is a problem here. What is the problem? The problem is that in terms of the DC point, if by now, I guess all of you are experts in analyzing the DC points of the transistor. You know how to find out the overdrive voltages, you know how to find out the currents to the transistor, and so on. Did you have a question? Or sorry. So if by now I'm assuming that you are experts in finding out the overdrive or finding out the currents to the transistors. Now there is a peculiar problem over here in this particular circuit that we just discussed. What is that peculiar problem? There is a tail current source over here, right? There is a current source connected at the tail, which is trying to fix the DC currents going through these two branches. The value of that DC current is equal to ISS over 2. Half of that DC current will flow through the left side branch, half of it will flow through the right side branch, assuming that the DC points at V in and V1 and V2 are equal, and assuming all the transistors are in saturation. Okay. So this is trying to fix the current as ISS over 2 for both of these branches. But at the same time, we just said that there is a current source on top over here because you're biasing this particular transistor. And as soon as you bias a particular transistor in saturation, that becomes a current source. There is no guarantee that this current source, so this actually works as a current source, right? If you assume that this transistor is in saturation, any transistor in saturation works as a current source. Right? That's just a property of a transistor. That's how the transistors are. Any transistors in saturation works as a current source. So if you have this transistor biased in saturation, and if this works as a current source, there is no guarantee that the value of this current is equal to ISS over 2. This transistor is trying to push in or trying to create a current in this branch. There is no guarantee that that current is exactly equal to ISS over 2. So basically, these two current sources are fighting with each other. The tail current source and the current source that you create on top, they will fight with each other. So that's a challenge. And of course, in circuits, as you know that if there are challenges, there are solutions as well. The solution is a little bit more complex. It is called a common mode feedback. So how you actually want to design these two current sources is that they will not be independent current sources. You want to design them as dependent current sources. That you take this particular current and then feed it back in a way that you ensure that the other current source, the current sources that you're connecting on top, are exactly equal to ISS over 2. So you need a feedback mechanism. So that is usually called a common mode feedback. Okay, we'll not discuss common mode feedback in this course because that's a much more advanced concept, a graduate level concept. But you should know that this is a practical challenge, that these two transistors or these two current sources will fight with each other. And the only way to make sure, or the only way to avoid the fighting between these two transistors is to make sure one of these current sources become a dependent current source. If both of them are independent current sources, then they will fight. If one of them becomes a dependent current source, they will not fight. And this is one way to ensure this is one way to do the common mode feedback. That's the solution. And I'll not go into details of how common mode feedback works. What you're doing in this case is that you basically take the DC bias points at the output terminal, right? So these are DC bias points at the output terminals. And the DC bias points, let's just for a second assume that these top transistors, or you are not biasing these top transistors. Your DC bias points at, let's say, point X and point Y are determined solely by this ISS current. Okay, if for a second, if you just assume that these are resistors, you know that the DC bias point at this point, at point X, is equal to VDD minus D times ISS over 2. Again, something we had discussed in class when we were discussing differential amplifiers. Let's just assume that this is true. So that's the DC bias point over here. Similarly, at point Y, your DC bias point should be exactly the same, assuming that the two branches are identical. Now, what you're doing here is that you're taking an average of those two DC bias points, and averaging is in some way low-pass filtering. Okay. So in terms of analog circuit, in terms of digital, if you want to take two values X and Y, and if you want to take average of that, what do? You take X plus Y and divide it by 2. In case of analog circuits, how do you basically take the average of these two quantities? You basically connect them, tie them up at the same point, right? So you short them so that whatever interaction that can happen between the 2 points can happen, and then eventually they will figure out a intermediate point between the voltages X and Y. So you kind of tie them up at the same point, but while you are tying them up, keep in mind that at point X and Y, it's not only the DC, you always have some kind of AC signal as well. Once you're doing the DC analysis, we ignore the AC signal. But if you put any kind of circuit component, the DC and AC will always be there at the same time. So if you have an AC quantity at point X and point Y, and you just connect if you just short point X and point Y, remember what was the purpose of this differential amplifier? The purpose was that at the output, if you had taken the difference of the AC signals, you would see a large amount of AC signals. That was the purpose. Now I'm saying that I'm just shorting the two outputs. So that will defeat the entire purpose of the differential amplifier. So you cannot directly short them. What you can do is that you can connect a very large amount of resistance and then a capacitance. So what that will do, that it will do a low pass filtering at this point, the point where you are shorting them. It will do a low pass filtering. So only the DC will be shorted, but the AC will not be shorted. So again, as I said, that this is a much more involved concept, so don't worry about it right now. Just remember that this is something that you do more in a graduate level class, but that is the reason why you have these resistances and capacitances, that you want to short the DC, but you don't want to short the AC. And once you do that, what you can do is that you can compare it with a particular desired amount of common mode that you want at the output. And you can have this, the output of this particular op-amp, you can feed that back as the inputs to the gates of the entry and input transistor. So in that way, you'll create a feedback which is dependent on the ISS current. So again, much more involved, much more complex concept. But the message that I wanted to get through to you is that if you don't have these current sources as independent current sources, if you can somehow make them dependent, then the fight between these two current sources will not be there. All right. So the next thing we wanted to discuss is basically a differential amplifier with a current mirrored load. And this is something we'll start discussing on Friday's lecture. And that will be the last thing that we discussed before we go into what is inside an op-amp. Because once we have discussed this, you can probably go through this PDF a little bit before coming to Friday's lecture. That once we have discussed this, you will exactly know what should be there inside an op-amp, stage by stage. What should be the first stage of an op-amp? What should be the last stage of an op-amp? What should be in between, and so on. Okay, so that's something we'll discuss in the next class. And in Monday's lecture, we'll look into an example how to design an op-amp.
Yeah, I kind of reworked it while you were explaining, and I ended up getting the.
Yeah, that's great. That's great. So that should be much more than the gain that you had earlier.
Yeah. Before I had a gain of -100.
I think the numbers make sense. It's 3.55. If I remember that these are the correct number.
I did want to ask about the GM. So like this GM is GM2, right? The transistor 2 up here. And this is the formula for GM, right?
Yeah.
G in this case is 3, right? Your source is 4, right? So I actually end up getting a negative GM2.
So yeah, that's a good point. So it's not negative. Like for example, it's the way you represent it. So this is a PMOS. So for PMOS, the formula is not VGS minus VT, it's VST minus VT, right? Or the absolute value of VGS minus VT. As I said, that the best way to consider these scenarios is that you just always take the absolute value of it.
Okay. So then it would end up being the same, the same GM.
Exactly. So whenever you see a PMOS, use the same formula that you use for NMOS, but with absolute sign. We use absolute sign.
If I were to rescan this and turn it in,
Yeah, sure.
would I still get full credit for it?
Sure. Thank you. So I think according to the syllabus, the final exam is on 4th of December. Yeah. Yeah. Oh, okay. So on Wednesday, I want to have a summary of this entire course, that what we learned and what we did for the entire course, and what could be some future classes that you can take to further the knowledge. So that's what I want to discuss.
So, I mean, I just wanted to, so what is for engineering? So, okay, so for right one, it's 0.2 of the amp so you can get the at the end it's the same like the first one it's gonna be 3 volts.
Yeah. So yeah, the DC point will be same as the previous.
But then here I get this. Well, necessarily like in reality, like I did not necessarily stay at 4 volts the first one. But I got here that So this is I didn't have to contract.
So you're saying that this point of quotient is not equal to 5 volts?
Yeah, no, it's not exactly like 1 volt. It's actually gonna be 5 minus R.
Yeah, I2 is something that you already know, that I2 is equal to this 40 milliamp. I2 does not, that's what is given in the problem.
No, I mean, they got different gigs. Different gigs. You gig one.
Oh, okay, okay, they are different.
Yeah, so I think one is 0.4 in out. But I mean, when I replied this, ES2 and then wrote it put it here, so you have I2, so you have like minus 5 minus 2.5 K I2.
Okay, so if you want to solve it, so you can do that, right? I mean, you see that there will be two possible values of I2. That's fine.
I mean, it's close.
It will be close. And we see two possible values of I2 for one, it will not be in the saturation region or cut off, it might go into cut off or drive region. For the other one, it will be in the saturation region.
I mean, it's kind of like the same, but a little bit different.
Yeah, I think you're doing a more exact analysis and that's fine. Yeah. Yes, yes. I think the board is right now with one of my students.